In this video, we prove a basic set identity involving functions. So let f be a function from domain X to codomain Y, and let A and B be subsets of the domain X. Then it is always true that the image of A intersection B is contained in the image of f of A intersection with the image f of B. So let's do this. We've seen before how we prove, well, there are many ways to prove set identities. You could do it also with truth tables and so on. But in this one, we're going to do it with element chasing. So we saw before how that works. So the basic idea of element chasing was that you start by taking an arbitrary point of the set on the left, and then you do a bunch of algebra and use rules and so on, and you end up showing that that point belongs to the set on the right. So let's do this. So proof. So let Y belong to f of A intersection B. So this is where we start, and our goal is to then show that Y belongs to f of A intersection with f of B. Okay, so let's start opening up what this means. So if Y belongs to f of A intersection B, then by definition, so what does this mean? By definition, there exists some X in A intersection B such that f of X is equal to Y. So once again, you can never prove stuff if you don't know all the definitions. And so there's really no way around this. To prove a theorem like this, you need to know the definition of a function, you need to know the definition of subsets, you need to know the definition of containment, you need to know the definition of the image of a function, you need to know the definition of intersection. If you do not know all of these definitions, it is impossible to do the proof. So you start by taking an element Y that is in the image of A intersection B. So once again, what does it mean that it's in the image? What is the definition of image here? The definition of image is that the image of A intersection B is all the elements in Y, in the codomain, such that there exists an element in the domain that belongs to A intersection B. So in other words, if Y belongs to the image of A intersection B, then there has to be an X in A intersection B such that f of X is equal to Y. Okay, so since X belongs to A intersection B, then by definition of A intersection B, then X belongs to A and X belongs to B. Okay. Thus, so what do we have? Thus, we have Y equal to f of X for an X that belongs to A. So this means that Y has to belong to f of A. So let's look at this carefully. So since X is in the intersection, then X is in A and X is in B. But we know that Y is equal to f of X and X is in A. So if Y is equal to f of X and X is in A, that means that Y belongs to the image of f of A. Why? Because for Y to belong to the image of f of A, it means that there exists some X in A such that f of X is equal to Y. So that's exactly what happens, and so you have this. Now, this is also going to be true for B, because it's also true and X belongs to B. So once again, similarly, since X belongs to B, we have y must belong to the image of B. But now we know that y belongs to f of A and y belongs to f of B. Hence, y belongs to f of A intersection f of B. And this proves what we want. So we took an element y on this set over here. So we took an element y in f of A intersection B, and we showed that it is always the case that when this happens, then y is also going to belong to f of A intersection f of B. And that is the definition of containment. And so with this, we are done.